Exponential functions are fundamental to all the sciences because a lot of real-world quantities grow exponentially. For instance, a virus left to its own devices will spread exponentially. Also, populations themselves grow exponentially until they run out of resources or something else interferes. When we say that something grows exponentially, we mean it can be modeled by a function like this. Some population after t days is a times b to the t. Notice that here a represents the initial population, the population on day 0, and b is really a ratio. It's the ratio of the population between any 2 consecutive days. The fact that this ratio is the same no matter which 2 consecutive days that you look at is what it means to be growing exponentially. Every day the population triples means that b would be 3. Here's a very natural scenario if you were, say, working in a biology lab. Let's say you're cultivating a little colony of bacteria, and you start out with 100 specimens. You know that this particular type of bacteria doubles about every 3 days. How many bacteria do you expect to have after a week? And when do you think you'll have at least 5,000 bacteria? Think about how you would approach the first question. You'll need to use this model for the exponential growth, and you'll need to use the exponential rules on your Precalculus fact sheet. The first thing you need to do is model the information you've been given. The fact that you start with 100 bacteria means what? It tells us that P0, which is A, equals 100. What about the information that the colony doubles every 3 days? The natural way to represent this is to say that 2 is the ratio of pt plus 3 and pt. And when you try to reduce this using the model, you should ultimately get that 2 is b cubed. And you're going to need to use the fact that b to the t plus 3 is b to the t times b cubed. So then, pt is a, which is 100, times b to the t. We know that 2 is b cubed, so what's b? b is just 2 to the 1/3. Using one of our other exponential rules, this is just 100 times 2 to the t over 3. Now we're ready to answer that first question. How many bacteria will there be after 1 week? The answer is just p of 7, which is about 504. What about that other question? We want to find a t so that 5,000 is p of t, is 100 times 2 to the t over 3. We want to isolate t. We start by dividing by 100. In order to get that t out of the exponent, we need something that undoes exponentiation. We need logarithms. So when we take log base 2 of this equation, on the left we get log base 2 of 50, and on the right, log base 2 undoes the 2 to the, and we just get that exponent, t over 3, by itself. Finally, we multiply by 3 to get that t is 3 times log base 2 of 50, or about 17 days. We're going to use exponential and logarithmic functions constantly in this class, so you should do several of the recommended problems from section 1.6 to practice using these exponential and log rules. But you also need to know what the graphs of these functions look like and how they behave. If the base b is bigger than 1, then the graph of y equals b to the x looks something like this. On the right, the function is growing rapidly as x gets bigger and bigger. On the left, when we put x to be a negative number, b to the x is becoming tiny. It's becoming close to 0. And this is producing a horizontal asymptote of y equals 0. On the other hand, if b is between 0 and 1, then the function is going to shrink very quickly, and it will have a horizontal asymptote at y equals 0 on the right. So why do the graphs behave this way? The key exponential rule here is b to the minus n is 1 over b to the n. For example, 2 to the minus 10 is 1 over 2 to the 10. 2 to the 10 is about 1,000, so that means 2 to the minus 10 is about 1 in 1,000, 0.001. So we can see here why, for 2 to the x, you get that horizontal asymptote y equals 0 on the left. What about when b is a half? Well, when we raise 1/2 to the 10th power, that's the same as 1 over 2 to the 10. And when we raise 1/2 to the negative 10, that's the same as 2 to the plus 10. Actually, the graphs y equals 2 to the x and y equals 1/2 to the x are mirror images of one another because of this log rule. We're allowing the base b to be any number between 0 and 1, or any number bigger than 1. If b was 0 or b was 1, b to the x is basically constant. Why can't we have a negative base? The trouble is that when x is a half, we get b to the 1/2, which is the square root of b. So when b is negative, this does not exist. There's a special base called e, or Euler's number. And the things that make e special really have a lot to do with calculus. We're going to learn more about that in sections 3.9 and 4.5 of this class. Remember the notation that log base e is called the natural log of x, and it's written ln of x. What does the graph of ln x look like? Well, since ln x is the inverse of the function e to the x, we can start with that graph and then flip it over the line y equals x. Every point on the graph of y equals e to the x is going to correspond to a point on the graph y equals ln x, just by switching the coordinates. E to the x is always positive. The range of the first graph is all the positive numbers. That becomes the domain of ln x, meaning you can't take the natural log of any negative number or of 0. What happens to the natural log of x as x gets close to 0? We get a vertical asymptote. The graph goes down to minus infinity, and that's corresponding to the horizontal asymptote we had for y equals e to the x. E to the x actually grows faster than any polynomial, and we'll see why in section 4.5. So what does that tell us about the natural log of x? When we take that really steep part of the graph, e to the x, and we flip it over, it becomes something that grows very slowly. We'll also see in section 4.5 that the natural log of x grows slower than any polynomial. Scientists estimate that there are about 10 to the 80 particles in the observable universe. That's a giant number. But if we take the natural log of it, log rules tell us this is just 80 times the natural log of 10, and that you can easily plug into your calculator and get about 184. So the natural log of basically the biggest number in the universe that really exists is only 184. So ln of x is growing incredibly slowly. Please go on to the next and final video of this set, which contains a brief review of trigonometry.